This is lecture 15 on limits of functions. So here's the definition. Let f be a function from D, and here D is assumed to be a subset of the reals. All right. That should probably be mentioned. That's our context at the moment. And x bar, a limit point of D. That means, of course, that the intersection of an open ball around centered at x bar and D has infinitely many points. We say that f has a limit at x bar if there exists a real number L such that for every epsilon greater than 0 there exists a delta greater than 0 such that f of x minus L is less than epsilon whenever x is in D and x is within delta units of x bar. So what this says is that you can go sufficiently close to x bar such that the values of f of x are as close as you'd like, to L. In this case, we write the limit as x goes to x bar of f of x equals to L, right? All right, so one important comment your textbook makes, which is a good one, is that the limit point here, x bar, need not be in the domain of the function, right? We can calculate limits of limits of a function at points which are just outside the domain. All right, and here's an example. And I changed the numbers in the textbook, so you'll have a couple of additional examples here. I will soon go back to the textbook, though, because it's pretty solid, and I think I don't really add much by writing their proofs out again here. So anyway, here's the example. So suppose you get a function from R to R, and f of x is 3x plus 2. So I'm not even showing you the scratch work here. This is just the proof, all right? And so as we're reading this, you might go, what? How did I think of that, you know? I'm not really explaining my thought process in developing the proof. I'm just showing you a proof, all right? Let epsilon be greater than 0. Choose delta equal to epsilon over 3. Again, why did I do that? Well, we'll see soon enough. Suppose we have a real number x, and x is within delta units of 6. You might also wonder, why did I choose 6? Well, I just did. All right, so this is kind of a bad example. I haven't told you what I'm trying to do here. I mean, if you want, I could improve on this example by adding a sentence at the start. Goal: show that the limit as x approaches 6 of, what was the function? The formula was 3x plus 2. 3x plus 2 equals 220. All right, that's the goal here, which I didn't bother to state at the start of the example. My bad. Anyway, so here we go. We've got f of x, f's value of f of x minus 20. Well, 3x plus 2 minus 20, and that gives you 3x minus 18. Factor out the 3. And of course, we can pull 3 outside absolute value by property of absolute value. And so we get 3 times x minus absolute value of x minus 6. But conveniently, that's less than delta by assumption, right? And we also made delta equal to epsilon over 3. So in fact, I have less than there, but to be more honest, that's not less than, that's just straight equal, isn't it? In fact, if I put less than there, it's incorrect. It's actually equal to, right? I guess I could have put less than or equal to, that would have been okay, but definitely less than is not correct. There we go, I fixed it. So we've just shown that for this choice of delta, whenever we're within delta units of 6, we have that the values of f of x are within epsilon units of 20. And it follows then by the definition that the limit as x goes to 6 of 3x plus 2 is equal to 20. All right. Now, so I didn't show you the scratch work here, right? But the way you actually work this problem is you calculate the difference of the absolute value of f of x and the limit value, which is in this case 20. And then you see how it works out, and you know that you get to make this, absolute value of x minus 6 less than delta, and then you choose delta as a function of epsilon so that you can achieve this difference being less than epsilon like that. let me show you another one that's more complicated. Example 2 in your book, example 3.1.2, is actually kind of a weird example. I'll let you look at that one, but that one's kind of odd. I'm skipping it. Instead, I'm going to show you a kind of more typical example here. I mean, that example in the book I'm talking about, example 3.1.2, it's a good example, right? But I'm going to go a different direction. So next up, suppose we have a quadratic. All right, quadratic. In particular, we have 3x squared plus 2x minus 1. I'm going to prove that the limit as x goes to 1 of f of x is equal to 4. Not surprising, right? Plug in 1 and get 3 plus 2 is 5. 5 minus 1 is 4. All right, so I made some scratch work in gray right here. So I calculate the difference of f of x and f of 1, actually, which is 4. And I could have just started with this, honestly. I'm not sure why I wrote that here. Sorry about that. It's not wrong, it's just not like totally logical. I really should just put this minus 4 and go from there at this point. Anyway, 3x squared plus 2x minus 5, that factors. It will always be the case that when you're working with one of these polynomial problems, you can like factor out x minus the limiting value, which in this case is 1. So I wrote x minus 1 here to start with, and then I knew that I'd be able to put something over here to make the factoring work. So sure enough, 3x plus 5 is the cofactor of x minus 1. And I say that that's less than 11 times the absolute value of x minus 1. It's not at all obvious from this line right here why I can trade my absolute value of 3x plus 5 for 11. But let me show you why that is. So to control 3x, the absolute value of 3x plus 5, it's helpful to assume that we're within 1 unit of the limit point. Just as a, I mean, you could assume you're within 2 units of the limit point. I mean, whatever you want. 1 is just traditional. So if I'm within 1 unit of the limit point, then I get this minus 1 less than x minus 1 less than 1, which gives me 0 less than x less than 2, which then multiplying, so I'm basically working to recreate 3x plus 5 here. So then multiply by 3, I get 3x less than 6, between 0 and 3x and 6. Add 5, I get 5 less than 3x plus 5 less than 11. All right, and so obviously you can put minus 11 on the other side. And so if we put it into our requirement for delta that the absolute value of x is less than 1, then we can force the absolute value of 3x plus 5 to be less than 11, as it happens. And okay, so, and if I can just point out, that's not terribly surprising, because if you think about absolute value of x minus 1 less than 1, like the biggest that is 2. And so if you think about plugging in 2 into this, you get 6 plus 5, which is 11. So it like makes a lot of sense that if you're ranging from 0 to 2, 3x plus 5 is ranging from 5 to 11. This is like totally unsurprising. All right, now here, so this is the scratch work. This motivates my following proof. So let epsilon be greater than 0. I'm going to choose delta to be the minimum of 1 and epsilon over 11. All right, so again, the proof has to be self-contained. The gray part is not part of the proof, all right? Sometimes I will skip some of the like obvious steps in the gray and give a more terse argument in the proof. Like, that's okay. So here it is, but not too terse. So delta the minimum 1 and epsilon over 2, epsilon over 11. Suppose 0 is less than x minus 1 is less than delta. All right, then that implies that we have 0 less than epsilon value of x minus 1 less than 1, which then we can unpack as minus 1 less than x minus 1 less than 1, which then implies that 5 is less than 3x plus 5 is less than 11, which then implies that the absolute value of 3x plus 5 is less than 11. All right, and of course we also have that the absolute value of x minus 1 is less than epsilon over 11 because delta was the minimum of 1 and epsilon over 11. So certainly if x minus 1 is less than delta, it's less than epsilon over 11. And so consider then the difference of f of x and 1. Sorry, I seem to, I'm actually, okay, fine. Well, the idea of looking at that instead of this it's a vestige of me having read a later section in the chapter. My apologies for this. I think I have like section 3.2 or 3 or 4 in my mind when I wrote this, but sorry about that anyway. So this, you could justifiably start with that right there, okay? Anyway, so that simplifies to this, which factors, and then that's less than 11, because we've just established that 3x plus 5 is at most 11 in absolute value. And then, of course, the absolute value of x minus 1 is less than epsilon over 11 as well. The 11's cancel, we get epsilon, and therefore we've shown that the limit as x goes to 1 of 3x squared plus 2x minus 1 is equal to 4. So these are pretty standard examples. When I teach Calculus 1 to like freshmen, I will actually do this kind of epsilon delta proofs in their class in my previous institution because that was part of the curriculum. So they're not hard. Anybody can do them. That's not true. Actually, 50% of the freshmen can't do it. They will always write the arguments backwards no matter how much you teach them. But let's just pretend everyone can do it. Woohoo! All right, so we're already kind of past this page. Truthfully, so here's the example I skipped. This one's quadratic, but it's kind of funny. The domain is 0 to 1, and that kind of because you might wonder why this example, the delta's epsilon over 3, and yet somehow he does a quadratic. Like typically quadratics, you got to do this minimum trick I just did. The reason they don't have to do the minimum trick that I just did is because the domain is carefully crafted to make this right here happen, which is ever so convenient. All right, that kind of argument is not plausible for most examples, because usually, well, if the domain is not, pared down, what I'm trying to say is that essentially what's going on in this example, with respect to the example I just gave, is that the delta being less than or equal to 1 is kind of implicitly hidden in their choice of domain. It's rather sneaky what they've done here. And anyway, so here's the next example in the textbook. And this example is very much the same song and dance as what I just went through. Okay, so I'll let you read it. Example, it's again, basically in the previous example, they factor the quadratic, and then they control one of the quadratics by making this minimum of 1 epsilon over 5 thing. But all right, let's look at example 3.1.4 though. That one should be a little bit different, but kind of the same song and dance. Let's see if I can find let's see here, maybe I'll write on, I'll write on here. Actually, let me just try to stick with I'm trying not to generate too much extra paper here. All right. I will eventually focus. Sorry, guys. So let f from the reals to the reals be given by 3x minus 5 over x squared plus 3. All right, great. Prove that the limit as x goes to 1 of f of x is minus 1/2. All right. So we're trying to look at, absolute value of f of x minus 1/2, and we're going to try to find an x minus 1 factor because we can control that because the limit point here is x is 1. So, all right, so you take that difference, which is 3x squared, and make a common denominator, right? So that gives me 6x minus 10 plus x squared plus 3. And, okay, so the numerator, and this will always happen. This is so cool, right? So that factors to x minus 1 times x plus 7. And because 3 minus 10 is minus 7, so x squared, yeah, sorry, I just have to write something. Where's my pen? I'm not writing anything terribly profound. It's this right here, right? Simplifies to x squared plus 6x minus 7. So it's obvious that you get that factoring, right? But you get to control x minus 1. That's less than delta, right? But then what happened to the x squared downstairs? Well, notice what's happened is by dropping the x squared, which is positive, right? We've made the denominator smaller by replacing it by 6, right? So by that kind of standard trick, we don't have to worry about that x squared plus 3 downstairs. Now, if you had a different example where you had like subtraction in the denominator, you'd have to think harder about what to do there, all right? So this example is kind of friendly in the sense that it allows that simplification. And then we're essentially back to the same kind of problem as we had in the previous example, because we've got this x minus 1, which we can make less than delta, right? And then we've got this x plus 7, which is not going to be small, right? But if we think about it, as long as we're within 1 unit of the limit point, right? Let me just draw a picture. So just to kind of give you a geometric argument. So here's my x bar, my limit point 1, right? And if we think about that, if we're within, going between 2 and 0, if we're in there somewhere, right? Then think about it. How big can x plus 7 be? It can be, well, it's smallest at 0, it's 7, right? And it's largest at 2, it's 9. So if the absolute value of x minus 1 is less than 1, you can pretty easily see that it's going to be the case that the absolute value of x plus 7 is less than, well, 9, I believe. All right. And as he argues here, right, proceeding as in the previous example, if this is less than 1, we get that. And so 0 is less than x less than 2, thus absolute value of x is less than 2, and, oh, see, he likes to use the triangle inequality rather than directly confronting the expression, but it's, to each his own, whatever. Absolute value of x plus 7 is less than 9. All right, well, we came to the same assumption. So then we're gonna choose delta to be the minimum of like epsilon divided by, I think, 9/6 and 1, and that'll make it work here. So 9/6 is 1 over 9/6 is 2/3, isn't it? So we agree. All right, so where was I? All right, so let epsilon be greater than 0. Choose delta to the minimum of 1, 2/3 epsilon. So if we're within delta units of 1, we get the absolute value of f of x minus 1/2 is less than this. Yeah, see, this is not, in my book, this is not a proof, right? I mean, it's fine this is a book, right? It's okay. This is not a bad example, but my point is the proper proof, it should have some of this stuff up in here in the proof itself. And so, like, I'm not, if I was to write this properly, I would do this. I would rewrite some of these arguments and, put it all together in one narrative. All right? But there it is. So that's less than 9, less than 9, so you get 9 over 6. That's less than 2/3 epsilon. So that gives us epsilon again. Okay, great. Let's move on. So you have these so what we've done so far is essentially just, direct proofs of a limit existing for a particular formula at a particular limit point, which is numerically given. And so essentially there, the name of the game is, given an epsilon greater than 0, you had to choose a delta, and go from there. But there's more in this section, and this is a big one. This is the sequential characterization of limits. And here we have f function from d to r and x bar the limit point. And the limit as x goes to x bar of f of x is equal to L if and only if the limit as n goes to infinity of f of xn is equal to L for every sequence x of n in d such that xn is not equal to x bar for every n, and xn converges to x bar. So let's see here how to say this. So basically you can look at sequences which approach the limit point, right, and yet don't get to the limit point. And if for all such sequences the image sequence f of xn converges to L, then it implies that the limit as x goes to x bar of f of x is equal to L. Now this is epsilons and deltas, right? This has nothing to do with sequences directly. So this is kind of an interesting result because we can look at sequences and get something about the, the limit, and vice versa. All right, so here's the proof. So the P, I've labeled this part P and the second part Q just to kind of guide our study of it. All right, so suppose 3.1 holds. In other words, suppose that the limit of f of x is equal to L as x approaches x bar. All right, then if we take a sequence in D with xn not equal to x bar for every n, such that the sequence converges to x bar, then given any epsilon greater than 0, there exists a delta greater than 0 such that f of x minus L is less than epsilon whenever x is in D and within delta units of x bar. So the reason that this statement is true is because we're assuming 3.1, all right? We're assuming the limit goes to L as x goes to x bar. Then there exists n in the natural numbers with 0 less than absolute value of x minus xn minus x bar less than delta for all n beyond some n. Why can we do this? Right? So, well, because remember we had xn as a sequence in D with xn not equal to x bar. Notice that xn not equal to x bar. The less than delta, that's possible because the limit of xn goes to x bar, right? That gives us the top inequality. But the bottom inequality, this right here, the reason that that's true is because xn equal to x bar would imply that absolute value of xn minus x bar equals to 0, right? But that can't happen, so we can justifiably put 0 less than that absolute value less than delta, all right? So this 0 less than absolute value is coming from the assumption that xn is not equal to x bar, all right? And then for such n, right? Anyway, so for such n, we've met the condition needed for the values of the function to be within epsilon units of L. And there you go. So that implies, of course, then that the limit as n goes to infinity of f of xn is equal to L, because we just furnished an n such that whenever we're beyond that n, we get that the value of the sequence f of xn is within epsilon units of L. And then the converse direction would be q implies p, but he uses the logical equivalence of q imply p with not p implies not q. Remember, q implies p, logically equivalent to not p implies not q. So here's the argument in that sense. So conversely, suppose that 3.1 is false, right? In other words, assume that the limit as x goes to x bar of f of x is not equal to L, right? That means that there exists an epsilon not greater than 0, such that for every delta there exists x and d such that 0 they're within delta units of x bar, and yet f of x minus L is not less than epsilon naught, which is to say that f of x minus L is absolute value is greater than or equal to epsilon naught, right? Thus, for every n, there exists xn and d. So he's going to then he's going to choose delta to be 1 over n just for the sake of specificity, right? Since it works for every delta, why not make delta equal to 1 over n? And of course, f of xn minus L is greater than or equal to epsilon naught, but notice that the Squeeze theorem gives us that xn converges to x, right? And we also have that it's not equal to x by the lower 0 less than absolute value of xn minus x bar. And so there you go. It's a sequence that converges to x bar, and xn is not equal to x bar for n, but that shows you that, he says this shows that 3.2 is false. So why does that show us 3.2 is false? Oh, because the limit would not exist, right? This would imply that there is a sequence meeting the determined condition of 3.2, and yet the limit is not equal to L because this is the case, right? So, and that proves that this. So this is a very useful theorem, and essentially, if I had to characterize the rest of this section, essentially what they're going to do, is use the fact that we've already proved theorems about sequential limits and just steal the results, transfer them over here wholesale to the study of continuous limits. All right. So that, by the way, that's a terminology I would suggest is that 3.1 is a continuous limit, whereas 3.2 is a sequential limit. Now, we use the word continuity for a different, more technical reason, but if I wanted a description of this, I would say it's a continuous limit. All right. So here's 65. Corollary. Corollary. Let's see here. Where was I? Making sure I'm not skipping a page by accident here. So corollary 3.1.3. Let f go be a function from d to r, and let x bar be a limit point of d. If f has a limit at x bar, then its limit is unique. All right. So he says, suppose by contradiction that f has two limits. All right. And let xn be a sequence in D with x bar removed that converges to x bar. Then by theorem 3.1.2, the sequence fn, f of xn, converges to two different limits, L1 and L2. And he says this is a contradiction to theorem 2.1.3. Well, give me a second here, folks. Let me unearth that theorem from my handy dandy notebook over here, if I can find it. Pretty sure I know which one I'm pretty sure I know which theorem that's going to be once we find it. It's going to be the limit is unique for sequential limits theorem. All right. Let's see here. So theorem 2.1.3. Almost got it. I'm getting there. Theorem 2.1. Yep. Oh, what do you know? What do you know? As I forecasted, theorem 2.1.3 says a convergent sequence AN has at most one limit. So, hooray. So this is the kind of systematic thievery I'm talking about. Okay. Any theorem we can write for sequential limits, we can kind of, within reason, transfer over to write a corresponding theorem for the continuous limit. Now, there is another way to prove this corollary, and I'm not sure why this. I don't know if I'm forgetting something or oversimplifying things or something, but we will soon have that the that the limit is linear. So like another way you could do it is, of course, we know that the limit as x approaches a limit point, we can prove this, of 0 is equal to 0, right? And we also know that f of x minus f of x is equal to 0, right? So once we have the limit law that the limit of a difference is the difference of the limits, it provided that they exist. Sorry, I had an extra parenthesis there, my bad. Then, of course, this would be 0 because of this argument right there. But that's also the limit as x approaches 0. I guess this just makes people nervous to write it this way, but it doesn't seem like you're saying anything, but you are saying something, because if these were two different values, right, if this was L1 minus L2, well, L1 minus L2 has to be equal to 0, so L1 equals to L2. So the limit's unique. This is the argument which was shown to me to prove uniqueness of limit when I had classes, and I like this argument. But whatever, let's move on. Corollary, excuse me, 3.1.4. We have a function goes from d to the reals, x bar a limit point of d, then x, then f does not have a limit at x bar if and only if there exists a sequence, not equal to the limit point. I need to come up with a term for this. Like there exists a I don't know. If I was teaching a class like person to person, I would get tired. I would come up with a term for this. So you have a sequence which does not match the limit point for every n, and yet converges to x bar, and the f of xn does not converge. So, like if you can find even one sequence which approaches the, if you got x bar here, right, and you got the sequence xn which converges to x bar, and yet when you look at the corresponding f of xn, they don't converge to L. I mean, maybe the f of xn just is all over the place, boop, 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 boop. And all of a sudden, I apologize, it would seem I'm indicating limits are, two-dimensional, and so sorry about that. Everything should be on a line, right, because we're one-dimensional at the moment. But of course, these ideas, spoiler alert, these ideas still make sense for n dimensions. With just replacing absolute value with vector length. So, sorry, my picture's two-dimensional, but if you could find even one sequence that did like this, and yet the sequence of values doesn't converge, well, done, game over. The limit does not exist, and so that's the point of this next example. Actually, we look at the Duralay function, which is a fun function. It's 1 for rational inputs. It's 0 for irrational inputs. So, so this QC, remember, is the irrational numbers. It's the reals minus the rationals in my notation. So what he does is he fixes an x bar, and he chooses a rational sequence Rn, and a irrational sequence which both converge to x bar, and he defines a new sequence by making it rational for the evens and irrational for the odds, but they both converge to x bar. And we proved previously that if the even and odd elements of a sequence both converge to the same limiting value, then the sequence converges to that limiting value. So he says, it is clear xn converges to x bar. Great, but on the other hand, if we look at the subsequential limit, the function at the even inputs to the sequence converge to 1. The function at the odd parts of the sequence converge to 0. And if we have two subsequent, I can't say words today, subsequential limits converge to different values, then it follows that the full limit of f of xn does not converge. Consequently, the limit of the Duralay function does not exist at x bar. Which x bar? Well, x bar was arbitrary. So this is an interesting function. If somebody says, hey, give me a function of an example, give me an example function which has every point in the reals being a limit point, and yet none of the limits exist. That's what the Duralay function does for you. So, and again, past here, I think this one here is the comparison theorem, right? So we have the limit of f and the limit of g, both are one is L1 and one is L2, and suppose that you have a delta ball around the limit point intersected with the domain, So the functions have a common domain D. And suppose that the functions f of x is less than or equal to g of x, then if that's true, basically what this is saying is if f is smaller than g near the limit point, it follows that the limiting values must be likewise ordered. So, the comparison theorem. And so what this proof says is, okay, so since these limits exist, they're sequential, their corresponding sequential limits exist, and the values at the sequential at the sequences also can be compared in the same way and are ordered as such. And then applying the comparison theorem for sequences, we get L1 is less than or equal to L2. All right, great. And then, but I think it might be instructive, maybe if I had more time, I might try to give proofs of these theorems just using the epsilon delta definition as opposed to running everything through sequential thievery. It's probably a good exercise for you as a student to try to prove these theorems using epsilon delta arguments, because you could do that. It would be a somewhat straightforward modification of the theorem of the proofs which were already given for the sequential theorems. Actually, those would make relatively decent test questions. Interesting thought. Anyway, so theorem 3.1.6, let f be a function, f and g functions with a common domain D, x bar a limit point of D. You got limit of f is L1, limit of g is L2, and the L1 is less than L2. And so this one says, okay, well, if that's the case, so notice the difference in this theorem and the last. This one is saying the limits exist and their limiting values are so structured. He says, well, then that implies that the values of the function were likewise ordered near the limit point, right? There exists delta greater than 0 such f of x is less than g of x for all x in the intersection of the delta ball centered at the limit point and the domain, the common domain of the functions. Cool. And of course, except for at the limiting value x bar. There we don't get to say anything, because limits consider points near the limiting limit point, but not at it. All right. A point which, if you've taken my Calculus 1 class, you've heard me say 1,000 times. All right. So here's the proof of that. Let's see here. So let epsilon be greater than 0. L1 plus epsilon less than, and well, it says choose epsilon such that that's the case. And that's reasonable because basically the limiting values which are given, and remember we're assuming that L1 is less than L2 if I recall correctly. My memory is worthless. Yeah, L1 less than L2. L1 less than L2 is assumed. So if you think about that, then L2 minus L1 is positive, right? So L2 minus L1 over 2 is a positive number, and you can certainly choose epsilon. Let's see here. So we can look at an epsilon which is less than that positive number. Okay, great. And there exists a delta greater than 0 such that L1 minus epsilon. So, fine. The first condition here is nothing more than f of x minus L1 less than epsilon. And we can make that happen because f of x goes to L1 because of the given limit for f of x being equal to L1. And the second condition here is just the unpacked version of g of x minus L2 being less than epsilon, right? And we can choose such a delta to make that happen because we're given, of course, that the limit as x goes to x bar of g of x is equal to L2, right? So that's why that can happen. So, great. And then for all x in the intersection of the domain with the ball centered at the limit point of the radius delta, and of course x not equal to the limit point. And then what's he do? He says add epsilon across this, I guess. So adding epsilon gives me, well, he's not even adding epsilon, just sorry, I'll get it eventually here. Where was I? this guy is this guy, right? And this one is this one. The middle equality is just common sense, right? Oh, wait, it's not common sense. It's uncommon sense. It's exactly how epsilon was picked to start with. It's this guy right here, right? That's this one. And but then that shows f of x is less than g of x, and so that's what we were setting out to prove for all the x which are which are close to the limit point but not equal to the limit point, right? Okay, great. Theorem 3.1.7, what we got here? Well, let f, g, and h be functions with common domain D, x bar limit point of D, and suppose there exists delta such that g of x is sandwiched between f of x and h of x, right? F of x less than or equal to g of x less than or equal to h of x for all x near the limit point but not equal to the limit point, and also in the domain of the commonly held domain of these three functions. Then if the limit of the outside functions f and h are equal to L, then the limit of the middle function exists and is equal to L as well. This is, of course, the Squeeze Theorem, right? Squeeze Theorem. And the proof is straightforward using, this is the sequential Squeeze Theorem, I think, and this is the continuous limit correspond to sequential limits theorem that was given in this section. So, yep. We adopt the following convention. We'll write the limit as x goes to x bar of f of x without specifying the domain D of f. Then we will assume that the expression in question, f of x, has the largest domain, which f of x is a real number. Oh, this is my comment I was making in like pre-calculus. I say we assume that the domain is greedy as possible, right? Make the domain as large as you can, given the expression. So if I'm taking the limit as x goes to 2 of 1 over x plus 3, then I'm assuming we're dealing with a function defined by 1 over x plus 3, and the domain is all reals except for minus 3. That's the greediest possible domain for f of x equals to 1 over x plus 3. F of x equals square root of x, well, the domain should be non-negative, right? So there you go. And I hope that's a good start. Again, I'm sorry I'm a little bit behind the videos at the moment. I will endeavor to catch up, but I think anyway, this is a good starting point. I mean, restarting point. So what am I doing? I'm trying to turn off the camera with my computer. It's not good. Thanks, guys.